Welcome to the Tech Study channel. So, in the previous class, we have seen half answer of 10th question, that is construction and working of MOSFET. So, which is about N channel E MOSFET. Okay. So, in this video, we will see N channel D MOSFET. It's a construction and working, and it's three regions of N channel D MOSFET. Okay. First, this video is fourth part of the eighth video, because in the first part we have discussed about BJT act as a switch and amplifier, and in the second part we have discussed about JFET act as a switch and amplifier, and in the third part we have discussed about N channel E MOSFET act as a switch and amplifier. So in this video we will see N D MOSFET act as a switch and amplifier. So first we will see what is transistor. So in this video what we will study means about what is transistor, what is FET, and what is MOSFET and types of MOSFET. Then E MOSFET we have already completed in the previous class, and we will study D MOSFET, working and construction, plus three regions of D MOSFET, plus graphs in in each region. Okay. So what is a transistor? Transistor is a fundamental semiconductor device used to switch or amplify electronic signals and power. So switching means switching on or off, and amplifying means increasing the strength of the signal. And then transistors are categorized by whether they are controlled by input current or input voltage. If they are controlled by input voltage, then they are called voltage control devices. Example, FET, field effect transistor. If they are controlled by input current, then they are called current control devices. Example, BJT, bipolar junction transistor. And then we will see what is FET. FET is a field effect transistor, is a voltage control three terminal semiconductor device used for switching or amplification. Okay. And then MOSFET is a one type of FET. So we will see what is MOSFET. MOSFET is it acts like an electric valve where a small voltage applied to gate terminal, we create an electric field which opens or closes the channel for current to flow between source to drain. So we will understand by using DMOSFET diagram, this definition. Then here is the DMOSFET diagram, N channel DMOSFET diagram. So here it is saying that small voltage at the gate creates an electric field which opens or closes the channel to for flowing of electrons from source, between source and drain. Okay. So now this is active device who can control flow of electrons. Examples, and using external voltage source. Examples, BJT and FET. And MOSFET is of two types, DMOSFET and E MOSFET. So These are further divided into two parts: N-channel DMOSFET, P-channel DMOSFET, N-channel E-MOSFET, and P-channel E-MOSFET. So, N-channel E-MOSFET we have already discussed. In this video, we will only discuss about N-channel DMOSFET. Okay. So first we will see the definition of DMOSFET. Definition is DMOSFET is normally on electronic switch. It operates as voltage control wall that can be either narrow or wide in the channel. So it is a normally on electric switch, means already uh, before applying any voltages VGS or VDS, it is on only, means the ID current flows in the circuit. So as voltage controlled wall that can be either narrow or wide in the channel. So in the DMOSFET, the channel is already exist. In the E-MOSFET, it does not exist. We have to create the channel first. So the channel is already exist in this DMOSFET. So here is the channel. It is already created. So we are using this gate voltage, means VGS, to increase or decrease the size of this channel, means increasing or decreasing the drain current. Okay. Then so the why the name is MOSFET means due to physical structure and how it operates. Okay. Metal refers to the metal gate terminal. Here is there, and refers to the thin insulating layer of silicon dioxide that separates the gate from the semiconductor P substrate. Means here is the silicon dioxide, this thin line, which separates the gate and P substrate. Okay. Then semiconductor refers to the base material P type. Here is the P type. And field effect. Field effect means the current between the source and drain is controlled by an electric field created by the volt applied to the gate. So here also it is saying same, that the current between source and drain is controlled by the gate. Okay. Gate voltage. Okay. Then the below point is common for both D and E MOSFET. That is, there is no direct electrical connection between gate and N channel because there is no direct current between gate and N channel. This is due to silicon dioxide layer. Okay. Due to SiO2, silicon dioxide. Here it is saying gate is here and N channel is here, and so it is saying that there is no direct electrical connection between gate and channel because in between silicon dioxide is there. Okay. Then which is why these are often called isolated FET. Here gate isolated isolated gate fit. So yeah, so why, which is why these are often called isolated gate fits. Okay. So I will explain the diagram now. Here is the source, here is the gate, and here is the drain. And P substrate is there, which contains majority of holes and minority of electrons. And N type means majority of electrons and minority of holes. And this is the pre-existing channel. Means before applying any voltage, these two voltages, this channel exists. Okay. And here is the silicon dioxide, gate terminal is there, and gate to source voltage is there, and drain to source voltage is there. Okay. Then so why it is called DMOSFET and EMOSFET means the N channel DMOSFET, a physical N channel already existed, that's why the device is initially on. So I have shown in the diagram now. And we are saying this because id current is flowing from source to drain, between source to drain, not from, it is between source to drain according to MOSFET definition. MOSFET definition, what it tells, we have to apply small voltage at the gate, so we can control the source current between source and drain. Okay. And we are depleting means emptying the existing channel of its charge carrier to reduce or stop the current flow. We are emptying the existing channel. This channel is there now, here to here. We are emptying existing channel of its charge carriers to reduce or stop the current flow, and by using VGS voltage. This is why the name is DMOSFET. Okay. And then we will see in the working of it how the VGS is helpful to reduce the current flow between two N regions. We will see in the working of DMOSFET. Next, a DMOSFET is unique because it can operate in both depletion mode, reducing the channel by using VGS voltage, and enhancement mode, increasing the channel. Okay. It operates in both modes. Okay. How we will see in the working only. Then we can't reduce the channel depletion mode, means depletion mode, in the E-MOSFET because initially there is no channel exist. Okay. I have shown initial diagram and final diagram of E-MOSFET also. In that so here is there E-MOSFET initial and final diagram. There is no channel between 2 and plus regions, and here we are creating a channel. Okay. And then that's why we can't reduce the channel. Okay. But in DMOSFET we can increase or decrease the channel. Okay. Then only we can enhance, creating a channel it to it, allowing to flow. of current, hence name is E-MOSFET. Means enhancing, means creating a channel in E-MOSFET, that's why the name is E-MOSFET. Then construction of D-MOSFET is same as the E-MOSFET. uh, so so construction is the gate is not directly connected to the substrate. Here the gate is not directly connected to the substrate, between silicon dioxide is there. Okay, it is located over silicon dioxide, as I have shown now, and width is 1000 angstrom, and there is no this is E-MOSFETs diagrams are there. So these are the E-MOSFET representations. D-MOSFET representations are these. Here is the channel, P substrate, drain, gate and source. P channel D-MOSFET and N channel D-MOSFET. The arrow mark is inwards for N channel D-MOSFET. The arrow mark is outwards for P channel D-MOSFET. And arrow mark indicates the current flow. Okay. And then two heavily doped N plus regions are placed in lightly doped P-type silicon substrate. Okay, one N plus region is called source and other is drain. They are separated by 1 millimeter. And silicon dioxide is insulating layer of width 1000 angstrom and also called gate oxide. Consisting considering two plates. Here is the diagram, gate and substrate plate. Considering two plates, one plate is metal contact of gate and other is substrate. Between them a silicon dioxide layer is placed and act as a dielectric. This combination is called parallel plate capacitor structure. And then here is the gate, here is the silicon dioxide and P substrate. Whole area is P substrate. So here is the gate and silicon dioxide and P substrate is there. So that's why it is uh, uh, the gate is considered as one plate and P substrate is considered as P substrate means only the just beneath region of this silicon dioxide is considered as positive plate. Gate is positive and P substrate is negative plate, and in between them silicon dioxide is there, that is dielectric. So this structure we obtain a parallel plate capacitor structure. So then we are here. So here the gate is act as a positive plate and substrate act as a negative plate and silicon dioxide act as a dielectric, where the silicon dioxide prevents current from flowing directly from the gate to the substrate. So this point is for E-MOSFET. If we convert in the D-MOSFET, then we will get where the silicon dioxide prevents current from flowing directly from the gate to substrate, or substrate, in the substrate place we can write N channel. Okay, and allowing electric field to build up instead. And then don't see these diagrams, you will confuse. These are E-MOSFET diagrams only. This is the D-MOSFET diagram. Okay, then we will see Working of DMOSFET. Uh, in the working also, 3 points are similar to the working of EMOSFET. So what are they means? Gate is a metal or polysilicon and heavily doped because to provide high conductivity, perfect conductor by functioning effectively to quickly transmit voltage signals. Okay, heavily doping increases the carrier concentrations. So I forget to explain why the N plus regions are heavily doped and why the P type material is P type substrate is lightly doped. Before this working, we will see why it is heavily and lightly doped. So N plus regions and P substrate are heavily doped and lightly doped respectively because N plus regions are heavily doped because it acts as a reservoirs of charge carriers electrons. Heavy doping ensure there are plenty of electrons available to be injected into the channel. Okay, consider up to here only. Okay, for DMOSFET. And because why we should not consider this statement means we have already have a channel, pre-existing channel, so we are not forming channel. Okay, then heavily doping uh, ensures a low resistance means ohmic connection between the metal terminals means silicon and source and drain and the semiconductor p substrate. So where the ohmic contacts are there, I will show in the diagram. In the DMOSFET, here are the ohmic contacts. The sliding lines we can observe here. Okay, these are the ohmic contacts. Ensures low resistance. So how it is ensuring low resistance means? So what it does means it provides a low resistive path for current to flow from N regions to P substrate for effectively flow of electrons from source to drain. Okay, so ohmic contacts which provides a linear low resistive electrical connection between the metal and semiconductor over the operating voltage range without significant rectification means converting AC to DC. Without that, it is providing linear low resistance electrical connection means flow of electrons between metal. Here the metal is ohmic contacts of source, drain and P substrate, and the semiconductor means P substrate. Okay, over the operating voltage range without significant rectification. Here are the N plus region and P substrate. These are the metal contacts. So it allows the low resistive electrical connection between these metal contacts and the P substrate. This whole is the P substrate. Okay, area. And in case of P type substrate, this is the metal contact means ohmic contact. Okay, which provides the low resistive path for electrons to flow or electrical connection into the N plus regions. Okay, then ohmic contacts are made up of metal means source and drains are made up of metals. When metal touches a semiconductor, a potential energy barrier forms. So here we are here I'm explaining about how these ohmic contacts are providing low resistive path for electrical connection. So when metal touches a semiconductor, a potential energy barrier forms. In a lightly doped semiconductor, this barrier is thick. Where this barrier will form means here here it forms the barrier. Okay. Electrons must have enough thermal energy to jump over the barrier to move from the metal to the semiconductor, and for conduction and conduction of channel between two n plus regions. So electrons must have enough thermal energy to jump over the barrier to move from the metal means n plus region to the p substrate, and for conduction and conduction of channel between two n plus regions. So that's why n plus regions are heavily doped, so that the barrier becomes thin, because the width of the barrier is inversely proportional to the doping concentration. And then p-type substrate heavily doped. If the substrate were heavily P substrate is lightly doped, because if the substrates were heavily doped, the gate would need a much higher positive. So here, if the substrates were heavily doped, the gate would need a much higher. So leave this point. This is for E MOSFET. So uh, if the gate voltage is negative, then it will attract the holes from the P substrate. Okay, and it will decrease the size of the channel. Okay, so in this way the conducting channel will decreases. So if it is heavily doped, the P substrate is heavily doped, then in case we are providing positive gate terminal, then so the positive gate terminal will attract the electrons of P substrate, so the conduction will be increases, conducting channel will be increases. And if in case of we applied a negative voltage to the gate, so it will what it will do, it uh, if we applied a positive voltage now, if we applied positive voltage, then it will attract the electrons and increase the conduction channel. If we attract if we uh, applied a negative voltage, then it will attract the more number of holes. So in this case, the if substrate is heavily doped, then the conducting channel will easily pinched off. So that's why P substrate is lightly doped. Okay, then we will see working gate is of metal or polysilicon. It is heavily doped because to provide high conductivity, perfect conduction by function effectively to quickly transmit voltage signals, heavily doping increases the carrier concentration, making the material conductive. And then to and the second reason is why it is heavily doped gate. So to narrowing the depletion width, when metal wire, where is the metal wire means this is the metal wire, which is gate to source metal wire, is a meet a semiconductor, means gate. Okay, a potential barrier naturally forms by heavily doping the gate material. The depletion region at this interface becomes extremely thin. So due to heavily doping the gate material, the depletion region at this interface becomes extremely thin. Okay, because the as I said, uh, barrier width is inversely proportional to the doping concentration. Okay, next next in the working, because the channel is already built in, the device is on even at VGS is equals to 0. Here in the diagram you have provided positive voltage. If we short circuit if we short circuit like this, then then also the current flows in the circuit. Okay, and by applying a negative voltage to the gate, we push electrons out of this channel. So how we will see later. Then first we will see how the depletion region is formed. Okay, here the depletion layers, it indicates it, this line indicates the depletion layer. Okay, the depletion region separating the n plus regions from the p substrate forms due to functional physics of p-n junction. As I've shown now, it is due to the p-n junction, reverse biased p-n junction. So here in the circuit, we have to observe source and p substrates are short circuited to maintain the p-n junctions reverse biased. Okay, these are the, this is the one p-n junction, p-n junction. Okay, so in the depletion region formation, the second point is in the regions where n plus material rich in electrons touches the p substrate rich in holes, a concentration gradient increases. Okay, means electrons naturally diffuses from n plus region into the p substrate, and the holes diffuses from the p substrate into the n plus region. Near the junctions interfaces, these diffusing electrons and holes meet and recombine, neutralizing each other. So here in the diagram, this is the depletion region. Okay, I am indicating it. Due to the diffusion of electrons into the p substrate and holes into the n type material. Okay, then as the mobile carriers, means charge carriers, means electrons and holes disappear through recombination, they leave behind uncovered immobile ions. So as I have we already know, p type materials contains uh, negative acceptor ions and positive holes, and n type materials contains positive donor ions and what electrons, free electrons. So positive ions are left in the n plus side and negative ions are left in the p side. So here is the positive ions means negative acceptors, and negative ions means positive donor ions. these are left in the n side. Okay, because it is a part of n type material, and negative ions means positive donor ions are left in the p side because it is a part of p type material or p type substrate. Okay, here in the diagram, here is the n plus region and p type region. Here it Here in the n plus region, it lifts the positive donor ions, negative acceptor ions, and in the p substrate, it lifts the positive donor ions. Means combining these two positive p type substrate and n type region is forming a depletion region. Means combination of these ions forming the depletion region. Okay, so then so these layers of immobile charged ions create an internal electric field that opposes further diffusion. Means diffusion of what? Charge carriers. Okay, electrons into the p type material and holes into the n type material, and the both p-n junctions are reverse biased. As we have seen, both p-n junctions, they are reverse biased. This area now depleted of, means emptied of mobile charge carriers, electrons and holes, is the depletion region. Okay, the depletion region exists around the channel also. Why? Because the entire n type region, which includes both n plus regions and plus physical channel connecting them. So here are the two n plus regions, and n channel is also there. So according to the according to we know, just the depletion layers should be formed at around the n plus regions only. Why the depletion region is around the n channel also means, here I am explaining this. Because the entire n type region which includes n plus regions and physical channel connecting them, is in direct contact with the p substrate. Okay, because this contact area forms a continuous p-n junction along the entire length of the device, a depletion region naturally develops along that whole boundary. So here the p-n junction is along the entire boundary. Why? Because n channel is sitting in the p substrate. That's why p-n junction is developed, and which is in reverse biased. So that's why depletion region is, due to the diffusion, the depletion region is developed. So as long as the n channel is sitting against the p substrate, the boundary will always act as a junction and maintain a depletion layer, as I have said now. Then we will see the function of depletion region. Okay, means the actual working of DMOSFET starts. So when we apply negative voltage to the metal gate, here we have applied, here I have applied positive voltage. You will reverse it, negative here and here positive. So then it will become, we are applying a negative voltage to the gate. So it pushes electrons away from the silicon dioxide. So we are here. When we apply negative voltage to the metal gate, it pushes electrons away from the silicon dioxide. So here is the silicon dioxide. This negative voltage pushes the electrons of this silicon dioxide into the deeper into the p substrate. Okay, here is the p substrate above the channel. Okay, so then hole recombination occurs. It leaves behind a region devoid of free charge carriers. Here the electron hole combination occurs because it is pushing electrons and p substrate having majority of electrons. So that's why the hole electron recombination occurs. It leaves behind a region devoid of free charges. So uh, this is the region where electrons are not present above the channel. Okay, this depletion region grows as negative voltage increases from the top near the insulator down into the channel. Means this depletion region, the above this depletion region increases with the increase in the negative voltage. Okay, and from top insulator which means silicon dioxide to the conducting channel, which narrows this conducting channel. Okay, so in the conducting channel what we have, electrons will flow. So the recombination of electrons and holes in the channel depletes the n channel of free charge carriers. So in the channel, free electrons will be decreased due to this electron hole recombination, increasing the resistance and decreasing the channel size, and hence current is low between source and drain. Okay, source and drain means here to here. Okay, here to here through the channel. Okay, then when we apply a positive voltage at gate, it acts like a magnet for negative charge carriers. It attracts minority carriers electrons from the p substrate and pulls more electrons into pre-existing n channel. Here the statement meaning: if we apply the positive voltage, as we have shown, as we can observe in the diagram, that if we apply a positive voltage, then it acts like a magnet to the electrons, so which attracts this p substrate electron and it moves towards the channel. So functioning of depletion region in the when we apply a positive voltage, so it repels holes in the p-type substrate further away from the silicon dioxide interface. So what the depletion region will do? It repels the holes in the p-type substrate further away from the silicon dioxide interface. So here is the depletion region above the channel, and below the channel is also there. It is very thin. Okay, so it repels the holes from the channel away from the channel. Okay, away from the channel in this direction. Okay, Instead of region depleted of carriers, we get a flood of additional electrons in the channel. This effectively eliminates any depletion layer that was restricting the channel. So more electrons are packed into the channel between source to drain. So low resistance and low resistance path will be generated and increases the channel size, and hence current is high between source and drain. Okay, then we will see what are the three regions of DMOSFET. They are cutoff region, active or linear region, and next saturation region. First, the regions are defined by how VGS means gate to source voltage and the drains to source voltage VDS influence the drain current. Okay, the first cutoff region. The resistor is off. The gate voltage is negative enough to repel all free electrons out of the channel. Means combination of electron and holes, pinching it off so no current can flow. So the gate voltage is high enough, negative high enough, which repels all free electrons out of the channel. As we have seen in the working, combination of electron and holes occurs. So when the all electrons of n channel are combined with the holes, then the cutoff region occurs. Okay, now then the condition is VGS is less than or equals to VGS off. This is the pinch off voltage. Okay, VGS is equals to highly negative, VDS is high positive, ID is 0. For example, VGS is minus negative and VDS is 10 volts and ID is equals to 0 microamperes. So pinch off voltage is minus 4 volts. So we have to check these conditions first. So VGS is less than or equals to VGS off, means VGS off means VP. Okay, then minus 5 which is VGS is less than or equals to minus 4. That is true, it is satisfies. And VDS with high positive 10. Okay, then ID 0, ID 0. Okay, this is satisfies. Then this VGS should be below the pinch off voltage where the channel is completely restricted, means there is no current flow. Okay, and then it is not this part, and we see the graph. Here I have drawn between drain current and drain to source voltage. So here is the line along with the x-axis. It indicates the cutoff region because there is no increase in the ID current, drain current. Okay, although there was an increase in the VDS voltage. Okay, and then active or linear region. The transistor act as a voltage controlled resistor. As we increase the drain to source voltage VDS, the drain current ID increases proportionally. So I am talking about linear region here. The transistor act as a voltage controlled resistor. So as we are increasing VDS, the ID current is increasing. That's why we are calling it as a voltage controlled resistor. Okay, in this in both in so in both the linear and active regions, VGS is medium to high, positive or negative. Okay, and ignore this one. Okay, so here I have written linear VDS is low positive, IDS is medium positive, and inactive VDS is high positive and ID is high positive. Okay, then here is the some more detail about VGS. That is, if positive, if VGS is positive or 0, then ID increases more. Okay, means it attracts the electrons of p substrates also. That's why the ID is more. Okay, if negative, then ID decreases, ID is low. Why? Because it attracts the holes of the p substrate. Okay, and then electron hole recombination also occurs, that's why. And the device will stay inactive as long as VGS is not enough negative to reach cutoff. Okay, VGS can be negative, but as long as VGS is not enough positive to reach cutoff. In the active region, VGS can be negative as long as VGS is not enough negative to reach the cutoff region. Hope you understand this statement. Then we have taken one example for linear and active region. For linear, VP is equals to minus 5 volts, VGS is equals to 0, and VDS 1 volt, and ID 4 microamperes. Very small here, and current is rising. So we have to see conditions are satisfied or not. So here VGS can be positive or negative, medium to high. So we have taken 0. Okay, it satisfies. Then VDS in the linear, so low positive and ID should be medium positive. So VDS is low positive 1 volt, and ID is medium positive, that is 4 microamperes. Okay, then in active region we have taken example VGS is equals to 0, VDS is equals to 8, and ID is equals to 10, it is 10. Okay, microamperes. So we have to see the, as we know, VGS should be high or low, medium to high, positive or negative in both active and linear. So it satisfies the condition. Then VDS and ID. In the active region, VDS should be high positive and ID also high positive. Here the VDS is 8 volts, so we get the ID is also 10 volts, which is a maximum voltage. So in the linear region, the condition this condition should be satisfied. VDS less than VGS minus VP. So where is the VDS? 1 less than VGS 0 minus of minus 5. How much? 6. 1 less than 6, that is true. Then it satisfies the condition. And then VDS greater or equals to VGS minus VP in the active region. So in the active region, VDS 8 greater than or equals to VGS minus VP 0 minus 1 second. Here also VP is minus 5. So if we check this, 8 greater than or equals to VGS 0 minus VP minus 5. 0 minus of minus 5 plus 5. 8 is greater than or equals to 5. Yes, true. Then active condition is also satisfied. Then saturation region. The transistor is fully on and act as a constant current source. Increasing VDS further does not increase ID. Okay, because the channel has reached its maximum carrying capacity for that specific gate voltage. Okay, then transistor is fully on and they act as a constant current source. Because in this region current increases and then becomes constant. That's why the lines are like this. Okay, and further increase in the VDS does not increase the ID. Okay, because the channel has reached its maximum carrying capacity for that specific gate voltage. Okay, the condition is VDS greater than or equals to VGS minus VP, and VGS should be positive or negative, maximum to high, and VDS is equals to high positive, and ID should be high positive. And to achieve medium to high current, VGS is 0 or positive. Okay, and example is VGS 0, VDS 8, and ID is 10 microamperes, steady and maximum. Okay, then this is the graph between them. So I didn't shown graph. This is the linear graph and this is the active graph. Here the current increases linearly with the voltage, and here the current is increases and then becomes constant. Okay, so here we have to check conditions. VGS is 0, that is satisfied, positive or negative, medium to high, and VDS 8 volts means high positive, and ID 10 volts which is high positive. Okay, then this is the graph for different values of VGS for minus 1, 0, 1, 2. Okay, and then it indicates that ID is increasing up to a certain point, then further increase in the VDS does not changing the ID current. Okay, it becoming constant. Okay, and then in the saturation region the DMOSFET act as an amplifier because the drain current ID is relatively independent of the VDS and is controlled by VGS, as we have discussed in the saturation. Because small changes in the input voltage VGS, gate to source voltage, result in significant changes in the output current. The device can effectively increase the strength of the signal. So that's why it is act as an amplifier. So that's it for today's class. If you feel this video is helpful, then subscribe, like, share and comment. If you have any doubt, ask me in the comment section. Thank you. I will see you in the next class. Bye.